In this follow-up video, we are going to generate some Lewis structures. Okay, we're going to need our periodic table to do that. And so we want to come up with what are the Lewis structures for these different molecules. So I'm going to start these. These ones are fairly easy, but I'm going to go ahead and do it in the full way. So we've got hydrogen bromide here, and what you need to do is to count up the number of valence electrons that you have. And you do that using your periodic table. So hydrogen has one valence electron. Bromine, right here, is going to have 1, 2, 3, 4, 5, 6, 7 valence electrons that we're going to be working with. So we're really just working with the S and the P electrons here. So we've got 1 and 7, a total of 8 valence electrons. So 8. I'm just going to write 8 electrons that we're dealing with here. That are involved in the chemical bond. And so then I'm going to write the skeleton structure for that. Okay, like that. And so the line that I've drawn here, that represents 2 of the electrons. So now I've got a total of 6 electrons that need to be filled in. Now hydrogen only needs 2 valence electrons. So we are not going to add any more electrons to hydrogen. We're going to add them here to the bromine. 1, 2, 3, 4, 5, 6. Okay, so that accounts for all of the valence electrons that we had. If you look for octets, you see that bromine's got 2, 4, 6, 8 electrons around it. It's got a full octet. Hydrogen has the 2 valence electrons that it needs. Okay. Let's do the hydrogen dihydrogen sulfide molecule. Okay, so you're going to get 2 valence electron. You're going to get 1 valence electron for each hydrogen atom. And then for sulfur, it's going to be 1, 2, 3, 4, 5, 6. 6 valence electrons coming from there. So we're going to have, again, a total of 8 electrons, right? Each hydrogen has 1, so there's 2, plus 6 valence electrons from the sulfur. Okay, so now let's set up the skeleton structure. The more electronegative atom is typically in the center, and then the hydrogens go around it. Okay, so when you have hydrogens in your molecule and an electronegative atom, the electronegative atom is the center of the molecule, and then the hydrogens are satellites. And I could have put it here, or I could have put it there. I could put it anywhere I want. It doesn't really matter because this isn't a three-dimensional structure. It's just a flat structure that we're just trying to keep track of the electrons. So once I get my skeleton structure picked out, I make bonds like this. So now by making a bond between the sulfur and the hydrogens, I've just accounted for 4 of the electrons. So I'm going to subtract those off, which means I've got 4 left. Now the hydrogens don't need any more electrons. They've already got 2. Hydrogen only takes 2 electrons. And so we've got 4 more electrons. Where are they going to go? They're going to go on the sulfur. 1, 2, 3, 4. And this is our Lewis structure for the dihydrogen sulfide. It's got 2 single bonds. The sulfur, you'll see, has an octet of electrons, 2, 4, 6, 8. Okay, so this is the structure that we wanted. For diatomic nitrogen, each nitrogen atom has 1, 2, 3, 4, 5 valence electrons. Okay, so we have a total of 10 electrons to deal with. It's homonuclear. Okay, so the skeleton structure is pretty easy to pick out. Okay, we're going to put a bond there. Subtract off 2. Now we've got 8 electrons to fill in. 1, 2, 3, 4. Let's make it symmetric. 5, 6, 7, 8. We notice that neither nitrogen has an octet. Okay, so we've accounted for all of the electrons, but neither atom has an octet. How do we fulfill an octet between each atom? We need to share multiple pairs of electrons. Okay, so I'm going to take this pair of electrons and I'm going to share it, and I'll take this pair of electrons and I'll share that pair. We're going to wind up with a triple bond, leaving behind a lone pair on each nitrogen. Okay, so this is the correct Lewis structure for nitrogen. I used multiple bonds to help each atom fulfill the octet rule. Count them out: 2, 4, 6, and 8. That's the same for both nitrogens. Okay. The silicon Tetrahydride, we actually saw that example on the previous one. Silicon has 4. Each hydrogen has 1, so we've got 4 plus 4, 8 valence electrons. The skeleton structure should have silicon in the middle. It's more electronegative than the hydrogens, so they go around. A skeleton structure, we want to connect these with bonds, 2, 4, 6, 8. We've already taken into account all of the electrons, so we're done. Let's take a look at this, this anion here. So we've got CHO2 minus. Carbon has 4. Hydrogen has 1. Each oxygen atom, I'm going to write it like this, 2 times 6. Okay, so that takes care of all of the valence electrons from the atoms, but notice that there's a negative charge here. So there's going to be plus 1 more electron. Okay, so we've got 12, 13, 14, 15, 16, 17, 18 electrons that we've got to deal with. What should be the structure, the skeleton structure? Well, when you've got oxygens present, the oxygens tend to go on the outside. Okay, so the carbon, the more electropositive atom, is going to be in the center, and we're going to have oxygen satellites, and then the hydrogen is also going to be a satellite, and it doesn't really matter where I put them. Now what we want to do is connect our atoms using bonds. So we're going to take care of 6 of the electrons. Okay, so subtract off 6. That's going to give us 12 electrons that need to go in. Hydrogen doesn't need any more electrons. You want to take these electrons and start distributing them to the satellites first, especially oxygen because it's more electronegative. So we're just going to start counting them out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we've already gotten rid of all of the electrons. So all of the electrons are on the board. Now we want to worry about who's got an octet and who doesn't have an octet. Well, we see that the oxygens have their octet. Hydrogen has 2 electrons like it wants. The carbon does not have an octet. How are we going to get carbon to have an octet and keep our oxygens to having their octets? You want to share multiple pairs of electrons. So I'm just going to take this pair of electrons and I'm going to share it between the carbon and the oxygen. So that's going to give me a double bond there. I'll have 2 lone pairs left on that oxygen, and then I'll have those lone pairs on this one, and then I'll have my hydrogen. And I should be putting a -1 to let me know that these are all charged. All right, it's an anion. Okay, now if you check here, carbon now has an octet. It's got 2, 4, 6, 8. Okay, so the carbon does have its octet there. This oxygen, 2, 4, 6, 8. It has an octet, as does this one. Okay, so here every atom has 8 electrons around it, which is what we want for most Lewis structures. Okay. Let's go ahead and look at this this cation here, this nitrogen-oxygen cation. Nitrogen has 5 valence electrons. Oxygen has 6. Because it's a cation, we need to subtract 1 electron. Okay, so we're going to wind up with 10 electrons. The skeleton structure is pretty easy to pick out, right, for a diatom. So we've got 8 electrons that we need to fill in. We're going to start with oxygen. 1, 2, 3, 4, 5, 6, 7, 8. Okay, oxygen looks good. It's got an octet, but nitrogen clearly doesn't. So how are we going to fix things? We need to share more electrons from oxygen to nitrogen. Nitrogen is missing 2 pairs of electrons from its octet. So we're going to take that pair, and we're going to share it. This is a cation. We're going to wind up with a triple bond between nitrogen and oxygen, lone pair on nitrogen and a lone pair on oxygen, and it's all a +1 cation. For the oxygen difluoride, okay, fluorine is more electronegative than oxygen, and so we're going to have oxygen in the center, and then the fluorines are going to be the satellites. We need to figure out how many electrons we should have. There's 6 there, plus 2 times 7, so we've got 14, 15, 16, 17, 18, 19, 20. Very good. 20 electrons. We just placed 2, 4 on the board, so we'll subtract off 4, giving us 16 electrons that need to go in. Start with the fluorines. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, we've just done all of the electrons now, and if we look, everybody's got an octet, right? Around oxygen, we've got 2, 4, 6, 8. Around each, shouldn't add more dots. Around each fluorine, we've got 2, 4, 6, 8, and it's the same for both of them. Okay, so the octet rule is satisfied for all atoms, and we've taken care of all of our electrons, so that's the Lewis structure for this one. Let's take a look at the next set of problems. Okay, so here we've got a couple of molecules that they want us to look at. They want us to do a bunch here. So it's HCN. We'll just start with that one. We've got 1 valence electron there, plus 4 coming from carbon, plus 5 coming from nitrogen, so for a total of 10 electrons. How should we set up the Lewis structure? Carbon is the more electropositive, so it's going to go in the center. We'll have nitrogen and hydrogen as satellites. And then putting in our bonds here for the skeleton structure takes care of 4 of the electrons, giving us 6 that need to go in. Hydrogen doesn't need any more. We'll start filling them in on nitrogen. 1, 2, 3, 4, 5, and 6. So that takes care of all of the electrons. Carbon here does not have an octet, so we need to share some of these. So we'll share that one. We'll share this pair. We're going to wind up with a triple bond between the carbon and the nitrogen, and a lone pair on the nitrogen. Another one that they wanted us to do here was the ethane, okay, H3CCH3. Okay, symmetric structure. Probably want to have a symmetric Lewis structure like this. Here's our skeleton structure. And count up the valence electrons. So we've got 3 times 1 plus 2 times 4 plus 3 times 1. So we've got 8, 9, 10, 11, 12, 13, 14. 14 valence electrons. If you count out the ones that I've already added, it's 2, 4, 6, 8, 10, 12, 14. We're done. Okay, so the skeleton structure that we came up with is the correct Lewis structure for this species. Let's go ahead and look at let's do ammonia next. We'll just do NH3. Okay, we get 5 from there, plus 3 times 1 from the hydrogen, so we've got a total of 8 valence electrons. Nitrogen goes in the center, the hydrogens are the satellites. That took care of 2, 4, 6, leaving us with 2 electrons that need to go in. We get a lone pair right there on the nitrogen. Okay, so that's the Lewis structure for ammonia. Let's go ahead and do carbon monoxide. We've got 4 plus 6 valence electrons for a total of 10. Skeleton structure takes care of 2 of them. Now we've got 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. So all the electrons are on the board. Oxygen has an octet, but carbon does not. It needs 2 more pairs of electrons, so we're going to make a triple bond, and we'll get this structure here for carbon monoxide. Everybody's got an octet. For carbon dioxide, we've got 4 plus 2 times 6, so 12, 13, 14, 15, 16. 16 electrons to deal with. Carbon in the center because it's more electropositive. The oxygens are satellites. We take care of 4 of electrons that way. We've got 12 more that we want to fill in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oxygens look happy, but the carbon needs 8 electrons. It's only got 4. So we're going to take 2 there and 2 from here. We're going to make some double bonds. Now everybody's got an octet. Here we have some anions. These are fairly straightforward. So this boron tetrahydride ion, you've got 3 coming from boron, plus 4 coming from the hydrogens, plus 1 because it's an anion, for a total of 8 electrons. Boron goes in the center. The hydrogens are the satellites. You'll notice there's 4 bonds that are formed, which takes care of the 8 electrons. So that's the structure for this guy. For the hydronium ion, H3O plus, we've got 3 valence electrons coming from the hydrogen, plus that would be 6 valence electrons coming from the oxygen, minus 1 because it's a cation. So we've got 9 minus 1 gives us 8 electrons. Oxygen's going to go in the center with the 3 hydrogens around it. Okay, you're going to form 3 bonds in your skeleton structure, so that's going to take care of 6 of them. 2 electrons left. Those go right on the oxygen, and it's a cation. So that's the Lewis structure for hydronium. And then for the chloride ion, we get 7 valence electrons coming from the chlorine, plus 2 times 6 for the oxygen, plus 1 more because it's an anion. So we've got 12 plus 8 is going to give us 20 electrons. We've got chlorine in the center. Oxygens go around it, make our skeleton structure. That's going to take off 4 of them, leaving us with 16 to go on. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. It's an anion. And if you look, everybody's got an octet. And so we don't actually have to do anything to this structure. This is the correct structure. There are many exceptions to the octet rule. Okay? Species that are called free radicals that have an odd number of electrons. You can never satisfy the octet rule when you have an odd number of electrons. So an example would be nitrogen monoxide. Okay, it's got 5 electrons coming from nitrogen plus 6 coming from oxygen. You're never going to satisfy the octet rule there. We also have electron deficient species where the center atom does not have an octet. So beryllium dihydride won't make an octet. Boron trihydride and boron trifluoride. These molecules exist, but they don't satisfy the octet rule. Okay, we call them electron deficient species. We can also have what are called expanded octets or hypervalent atoms. These occur for atoms that have nearby empty d orbitals that can be used to take on more electrons. Examples: sulfur, phosphorus, and selenide or selenium. They often have hypervalent structures, and so we'll watch out for those guys. And so here we're just going to do several examples. So here we're looking at phosphorus pentachloride. Okay. Phosphorus has 5 valence electrons. Each chlorine has 7. So we've got a total of 40 valence electrons that need to be employed here. And so we've got phosphorus in the center, and then we're going to have 5 chlorines going around it. So we'll make a little pentagon here of chlorines, and then we'll make our structure, our skeleton structure. So notice that's 2, 4, 6, 8, 10 electrons that we've taken into account. We've got to fill in 30 electrons, and we start with the satellites. Okay, so 1, 2, 3, 4, 5, 6. So we have 5, and we put 6 on for each, so that's minus another 30. We just put 30 electrons on there, so we're down to 0. So we put all of the electrons on the board. This is the correct Lewis structure. If you look at phosphorus, 2, 4, 6, 8, 10 electrons. Phosphorus is a hypervalent species. It defies the octet rule. Okay, so phosphorus can break the octet rule, as can sulfur. Sulfur hexafluoride, this molecule exists. 6 valence electrons for sulfur, plus 6 times 6 for the fluorine, so we've got 42 electrons that we have to worry about. Sulfur is the more electropositive, so it goes in the middle, and we'll make a little hexagon of fluorine atoms around the center atom. We'll make our skeleton structure. Okay, so that's 2, 4, 6, 8, 10, 12. Okay, so we're going to have 30 electrons that need to go on here. Each of the fluorines is going to get 6 electrons. Right, we've got 6 of them. Looks like I miscounted. Let's see. So, yeah, 6 times 7. Each fluorine has 7 valence electrons, so I got that one wrong. So we've got 42 plus 6, 48, minus 12 is going to give us 36. I just put 6 electrons on each of the 6 fluorines, so that's minus 36 down to 0. So this is the correct Lewis structure here. Let's see, we've got another one that we want to do, the Iodine Pentafluoride. Okay, iodine is a halogen. It's got 7 electrons. Plus we've got 5 fluorines. Each of those have 7 electrons. So we're at 35, 42. Yes, 42 electrons. Iodine is more electropositive, so it goes in the center. Then we're going to have the fluorines. We'll make our skeleton bonds. Okay, so that's going to take into account 10 electrons. So we've got 32 electrons that need to go on. Now we're going to put those on the satellites first. So each fluorine is going to get 6 electrons. So it's 6 times 5, that's 30. So we've got 2 electrons left over. Where do they go? The only place they can, on the center atom. We see iodine here has 2, 4, 6, 8, 10, 12 electrons around it. It's a hypervalent atom. It has empty d orbitals that it can use to accommodate more than 8 electrons. Right? The reason we have the octet rule is because it takes 8 electrons to fill the s orbital and the p orbitals. But if you've got an atom here like iodine, okay, it's got empty d orbitals down here that are nearby in energy. It can use these empty d orbitals to accommodate electrons, and so it can form more than, it can have more than 8 valence electrons around it. Okay, so these are examples of hypervalent species. Here we have, these guys are also hypervalent, these xenon compounds. Most noble gases do not form compounds, but xenon can form a few. Okay, and so here's some examples of hypervalent species that I'll let you work on. Sulfur tetrafluoride is another example. Of a hypervalent species. I'm going to do one that is, I'm going to do this beryllium dichloride, which is an example of an electron deficient species. Okay, so in beryllium dichloride, we've got 2 valence electrons coming from beryllium, and then we've got 7 from the chlorines. So we've got 16 electrons total, 16 valence electrons. So the beryllium goes in the center. You've got the 2 chlorines in the periphery. The 2 skeleton bonds take into account 4 electrons, leaving you with 10 that need to be filled in. No, that was right before. 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You see that the chlorines, both chlorines have an octet. The beryllium, it only has 4 valence electrons around it. It's an example of an electron deficient species. I'm going to go ahead and leave these ones as exercises for you as well. And I'm just going to mention a couple more. I'm going to mention boron trichloride. I'll make it easier on myself. We'll make it boron trihydride. Boron has 3, and then you've got 3 valence electrons coming from the hydrogens for a total of 6. Boron goes in the center. Here are your skeleton bonds, -6. Okay, takes you down to 0. This is all you get for boron trihydride. You see that boron is electron deficient. Okay, so species can be hypervalent and take on more than 8 electrons, or species can be electron deficient and take on fewer than 8 electrons. Okay, so there's lots of exceptions to the octet rule, but the octet rule will work for many, many compounds as well. Okay, so I am going to stop this video here, and we'll pick up on some additional Lewis structure concepts in the next one.